Konnichiwa. My name is Marcel Beemster. I'm the CTO of Solid Sands, and today I'm representing Fujitsu Satsubi, our partner in Japan. I'm going to talk about compiler qualification using a test suite that's based on the language specification. Compiler safety is extremely important. You see here many companies that are our customers. They are based worldwide. Some of them are developing their own compiler tools. Others are using compiler tools. In all cases, they take the safety of the compiler very seriously, and they use our tools to do so. Customers in Japan on this slide are Denso, Rome, and Renesas, for example. The compiler is probably the most safety critical software tool that application developers use for automotive software. So all the source code of the application that goes into the car or any component in the car has to be compiled by the compiler. If there's a defect in the compiler, that means that there's a defect in the generated code. And that means that basically the component can do any safety critical, can have any safety critical impact. And that's not good. Verification of the compiler, qualification of the compiler can seem like a daunting task. Compilers are very complicated. They're very complicated to set up and use as well. And so this is a difficult problem. However, it's quite manageable if you have the right tools. And we need to start with the specification. On the one side, we have the specification of the C or C++ language. That's an ISO standard. On the other hand, we have the ISO 26262 specification about functional safety processes for automotive software and hardware. If we take ISO 26262 and look at clause 11 in part 8, that's called confidence in the use of software tools, that is the clause that is applicable to compiler qualification, because a compiler in this case is also a tool. The qualification process has 5 steps. We start with planning of the uses of the compiler, then the tool evaluation, the compiler evaluation, the qualification methods, we select which one we can use, then the actual work goes into the validation of the compiler and analyzing any defects, and then finally we have to write reports and review the whole process. Now the first step is actually quite simple. It's a straightforward step. You have to write down exactly the tools you use, the target that you're compiling to, and also the compiler options are very important for this step. But then we get to step 2, and that's a bit more tricky. Tool evaluation decides how you're going to qualify the compiler, and that decision process has 3 inputs. The ASA level, which actually turns out to be not so important, and then the tool impact level and the tool error detection level. The tool error impact level here is for a compiler almost always TI2, and that means that if there's a defect in the compiler, that can have introduce a safety hazard, and that makes it TI2. Now clearly, if there's a defect in the generated code, that is what can happen. Tool error detection needs a bit more explanation, and that is because how sure are you that your application tests can generate, will actually find all of the errors that the compiler may have. That's a very tricky question. You may think, okay, I have my test suite for the application with all the unit tests, full MCDC coverage for my source code. That must be sufficient to find any errors in the compiler. But that's not necessarily true, and I'll show you why. Here's a simple loop compiled with a low optimization level. We have one unit test case. We call the function f with 1. And then if we analyze that, we find that we have full MCDC coverage of the source code. If we look at the assembly code here, then we see that if we do the same analysis, all the instructions are executed, and also the branch that's in here is executed in both ways. So that's important property, and we have a good unit test also for the assembly code. But if we compile with a higher assembly level, then we see that much more code is generated, and the unit test only covers a few parts of that. Here at the beginning there is code covered, and here at the end there's some code covered, but there's a lot of black instructions here, and they're not executed by this one unit test. To actually have the maximum coverage for this piece of code, we need at least 5 unit tests. And even then, we will find that there are 2 branches here in red, this one and this one, that are actually not coverable in both ways. And the reason is that they are redundant branches. They can never be called in the other way. And that's slightly inefficient, but it means that if we are looking for a unit test to find maximal coverage, we can never find 100% coverage for this relatively simple example. And that means that even for this simple example, you would have to manually analyze why full coverage is not needed. Now, of course, we don't want to do that. ISO 26262 also doesn't require you to do analysis of assembly code. However, we have here a lot of generated code by the compiler, and we want to make sure that it is actually verified. So what we've done in SuperTest is provide a special test suite for loop optimizations. We have first created a list of all possible optimizations in 3 different mainstream compilers. Then we have looked at all the non-loop optimizations, and we have verified that our standard test suite triggers them all and also verifies that they are correctly executed. Well, what does triggering mean? It means that we have verified that the test, when it's running with and without optimization turned on in the compiler, generates different code. So that gives us an idea, well, this test is activating that particular optimization because the code is changed by the optimization level. Then for all the loop optimizations, we have done the same extensive analysis of all possible optimizations. And in addition, we have done this assembly code coverage analysis as well. So we have created enough unit tests for every loop optimization so that we get maximal coverage of all the instructions and the branches. And in the case where it's not 100% coverage, we have analyzed the cases and looked at the reason why that code is not coverable. So you can find more details about the optimization tests in the SuperTest manual if you're interested in that. So in the tool evaluation step, the tool error detection, you cannot be so confident that all the errors will be found by the source code unit test. And therefore, conservatively, we would pick tool error detection 2 or 3. And that means that we have to qualify the compiler using one of 4 methods. So there are 4 methods of qualification. And actually, there's not so much choice because 1, 2, and 4 are not really applicable. Either you can use confidence from use, but as soon as you change the use case or update the version of the compiler, that's no longer valid. And the other 2 require insight in the development process of the compiler. That is not always available to you. So what's left is validation of the tool using a test suite that's based on the language specification. And that's the method we're going to discuss further. So what you need to do for the validation of the tool is to establish that it is compliant with the specification of the functional behavior of the compiler in the language definition, the C or C++ standard. And you have to do that for the specific use case, so for the specific options that you use. We've already seen a different kind of options can result in usually different generated code. We also have to verify what the compiler does for ill-formed programs. If there's a diagnostic required, that's written in the language specification too. And we have to verify that we do get the diagnostic there. Otherwise, an ill-formed program may be compiled by the compiler. And by definition, it does not have a meaning. It does not have a functional implementation. But Some code is generated and it will do something, but not necessarily what you expect. And finally, if there are defects in the compiler, we have to define workarounds called mitigations. For any defects, you have to help the programmer and tell the programmer of the application, well, these are the steps that you need to take to avoid these defects. The test suite like this is based on the V model, and it provides the requirement traceability from the tests here on the right side back to the language specification on the left side, and also vice versa. For every section here in the language specification, we expect tests to exist in our test suite. And that's exactly what we've done. And in the reports that we generate, we can see also how that works. We can see that for every section, all the tests are passed, and sometimes they're not passed. There can be a defect, and then the nature of the defect is reported as well. So that brings us to the final reporting and mitigation. Obviously, you have to write down the results of the test and also the process that you followed to do the validation. That all becomes one report. The content of that can follow what is described in the ISO 262 documentation standard. And also we have to then specify for the defects that we have, what are the workarounds, the mitigations for the programmer. That becomes the safety manual for the compiler user. So for now we've talked about compiler qualification, but the language implementation actually consists both of the compiler and the library. What about the library safety? Well, library safety is a bit different. It has a different clause in ISO 26262, actually complete part, and it requires more extensive requirement traceability. We have to be more careful about the exact requirements. We have to show, we have to also show coverage of the library, and so that is a more extensive process, still doable, and we support that with a different product called SuperGuard. Right, that's the end of my presentation. You can contact Fuji Satsubi if you want to have more information about any of the topics that I talked about, or if you have any other questions. And thank you for your attention. Oyama shimashita.